Okay, today we're going to start talking about how do we create digital circuits. So digital circuits are really created by coming up with a Boolean algebra. Where Boolean algebra is going to be some type of logic statement that we're going to be creating. So logic statements are really made up of three basic conditions. These conditions are going to be called gates when we create a digital circuit. So what are the three basic gates that we have? So the three basic gates we have is an AND gate, which is drawn with a symbol that's kind of like a box. In your book, you will also see it that it'll have a little dot inside. We have an OR gate, which will have a little plus inside. And then we have a NOT gate, which is a triangle with a circle below it. Each of these items make up some type of logic statement. So a logic statement is an expression you're trying to do that forms up that you'll get a result based off of some type of input. So, for example, let's say we're talking about a little kid. You might tell the kid, I'm going to give you ice cream. So, giving the ice cream, that's your output. That is something they will receive. Now, there's going to be some conditions that this kid's going to have to do in order to get the ice cream. The AND gate would be you need to clean your room and feed the dog. Those are two things that have to be done in order for the kid to get an ice cream. The OR gate is that you want to give the kid an option. You might say, I'm going to give you ice cream if you do one of the following. You either clean your room or you go feed the dog. It's an option that we're giving somebody to do. Not gate is just that you're trying to tell somebody to do the opposite. So it's like, I am not talking. Yes, you are talking, it'll be something that'll be opposite. So we'll go through these examples. So let's first start up with an AND gate. The AND gate, you can see we have our symbols. This symbol is going to be broken up into two different parts. On the left side, here in red, I say that we have an inputs. Our inputs into this AND gates are A and B. Our output is the Z, and that's in the green. So the top one is an example of what we call a two-input AND gate. That is two conditions that we're checking. So in the example we were doing, Z, that's the ice cream. The A, this is clean room. The B is feed dog. You have some inputs that it has to be accomplished in order to get the value. Below it, we have a three-input AND gate, so it could be extra conditions. It could be, again, I'm going to give you ice cream, but you got to clean the room, feed the dog, throw the trash out. All three conditions must be met. So one thing that we can do with these AND gates and Boolean expressions in general is we want to describe how they're going to work by creating what we call a truth table. But this truth table is going to be the mapping of an input to an output. All right, so we have our truth table. So if you can look right here, this truth table, it will form like a T. On the left side, we're going to have input. We're going to have some binary value. On the right side, we're going to have output. We're also going to have a binary value. All right, in your book, you would see that we can form these gates up with some type of switch type of circuit. So in these switch type of circuits, we have our Z, which was our output. We had inputs of A and B, and these inputs are on switches. And at the beginning of this gate, we have some type of voltage. Usually we'll talk about, 5 volts, 3 volts, 2 volts. You have some type of voltage, and you want to see what happens on the output. The output, if it gets any type of voltage, we can say it's a 1. If it gets no voltage, we can say, okay, this is 0 because no voltage was seen. We're going to control these A and B based off of some type of signal. That signal is going to be a 0 or a 1, where the 0 is going to be, you can view it as being it's off, a 1 is on. A 0 is low, a 1 is high. A 0 is false, a 1 is true. You're looking at two opposite values. So on this switch, we can see if A is 0, we're going to keep the switch open. That means anything of the voltage flowing is going to get stopped. It's not going to continue on. Or we can say the voltage, the input is a 1. We're going to close the switch, and we'll see that the voltage will flow all the way through. Okay, so that's going to be how we control these switches, the 0 or the 1, the high, the low, the false, the true. Okay, so let's make up our truth table. When you make a truth table, remember again, you're going to list inputs on one side. You're going to list outputs on the other side. And the way we're going to write down our truth table is we're going to write all the combinations. The way you can kind of view it is if you want, do decimal numbers, do 0, 1, 2, 3, so on, depending on how many you need. And then you're going to convert these into a binary. So a 0 is 0, 0 in binary, a 1 is 0, 1 in binary, a 2 is 1, 0 in binary, and a 3, that's 1, 1 in binary. So those are the different conditions, and we're going to see what our output would be. So let's take this first circuit here, and I'm going to have voltage come in. A is a 0. Well, I stop. I can't move through. So if A is a 0, and in this case here we have B is a 0 as well, well, our output would be a 0. All right, let's look at the next condition. A is a 0. Oh, I get stopped. Even though B is closed, no voltage ever hits the output. So that would give this Z. I don't have one for when A is 1. So let's just do A is 1. So A is 1. We'll leave B as 0. Okay, so what do we expect on our output? Voltage flows and then gets stopped at B. So we would see a 0 on the output. Then we will have our last one of A is a 1 and B is a 1. You see our voltage flows, A is closed, we keep flowing, B is closed, we keep flowing, and then at the end, we will get our output of 1. So again, this is our example. We said a logic statement to a small kid. I'm going to give you ice cream if you, A, clean your room. The room was clean. That part of the switch closed. You feed the dog. That's B. That part of the switch is closed. Now, the key item is if you really want to look at how to evaluate an AND gate, if all the inputs are 1, your output is going to be a 1. Any other case, it's a 0. All right, so let's say we had a 3-input AND gate, A, B, and C. We're going to form up our truth table again. Remember, we do input on the left, output on the right. We're going to fill it in. Just number everything 0, 1, 2, 3, 4, 5, 6, and 7. The key thing with digital circuits is when we start counting, we always count starting with 0. It's a little bit odd from what we do in normal life, but that's the way we do it. So we take 0, figure out what the binary is for 0, 0, 0, 0. 3 is 0, 1, 1. 7 is 1, 1, 1. We would just fill in every input. And then we kind of think about these gates. In order for these gates to work, voltage has to flow. A has to be closed. B has to be closed. C has to be closed. That's the only condition where we're going to get an output of 1. So the kid will get ice cream if clean the room, feed the dog, took out the trash. And we can keep adding in more and more inputs. It's just always going to be one single output of a 1. All right, now we can move over to OR gates. And OR gates, you'll see the symbol with a little plus in it. We usually use a dot, like multiply for an and, a plus for OR. So we have an example of an OR gate. It has A and B, and we have Z. from our example, we said, okay, we're going to tell the kid you can get ice cream if you do one of the two items. You clean your room or you're going to feed the dog. So if we draw a circuit with these little switches, now we're going to have two parallel paths. The A path says you clean the room, and the B path said you fed the dog. Only one of these has to happen. So if we look at what our options are, you can flow data through. The kid did not clean the room, did not feed the dog. We stopped. No ice cream was given. Or we can start flowing data in. The kid did clean the room. Okay, you get ice cream. Doesn't matter if you didn't feed the dog. That switch could stay open. Or it could also be that the kid ended up doing both. It cleaned the room. We got ice cream. We fed the dog. We also got ice cream. So we can follow the paths to get to our desired result. All right, so what does the truth table look like? The truth table is inputs A, B, and then the output Z. Since we're using an OR gate, you see that I'm going to write it as it's A plus B. That's the way we can write an OR gate. So in the OR gate, the only condition that we only have a 0 is when you didn't do either of the cases. If we go to a 3 input, A, B, C, you see we write it as A plus B plus C. And again, there's only one output of a 0. That's when you did none of the options. Okay, our last one is a NOT gate. A NOT gate's a little bit harder. There's no real good logic item of testing, with like a kid with the ice cream. The idea is a NOT gate does a negation. It will flip the value. So you usually see it. It's only going to have only ever one input and one output. So the item is if you give an input of false, your output is true. If you give an input of true, your output will be a false. So when we make the truth table, the NOT gate, I'm going to write it out in the videos as it's an A bar. In textbooks, usually the little bar is a little difficult for text to be written. So you do it with an A with like an apostrophe, and that shows that you're taking the inverse of the negation. So if we get an input of 0, we get an output of 1. We get an input of 1, we get the output of 0. So those are the 3 basic gates that we're going to start forming with. We're going to take all of these gates. We're going to use it to form up some logic expression that we want a circuit to solve. And then from that circuit that we solve, we're going to try to do some math operations to try to make our logic a little bit more simplified. Now, I give you a basic logic example, ice cream, a kid. So you kind of say, okay, how does that work with a circuit? Well, the circuit might be, I want to turn on an alarm. I turn on the alarm if, I can detect that a window was broken or a door is open. That's an or to say an alarm has to go on. I might say, an alarm can go on only if the house alarm was armed and a window was broken. So we can kind of see how we can form up logic in order to create, like a real life example of a circuit. All right, so that's our basic gates. And then next class, we'll start looking at what we can do with these type of logic expressions.